So thank you very much for the kind introduction. Welcome everybody to my talk. I'm happy that so many made it back from lunch in time, and I'll do my best to present the research activities that are going on in Yelena's group at the moment. So in our group, we're interested in all sorts of fundamental nanoscale and quantum photonics phenomena, such as quantum optics, cavity QED, and nonlinear optics, as well as their application for practical devices, such as optical interconnectors in computers, optical quantum networks, nonlinear optical devices, and even biophotonic applications. So in my talk, I'll mainly talk about the coupling of self-assembled quantum dots to photonic crystal cavities, but the second part of the talk, I'll also present several recent results from Yelena's different other projects. So the quantum dots that we're using are self-assembled indium arsenide quantum dots in a gallium arsenide matrix. They have a typical lateral dimension of 20 nanometers and a typical height of 5 nanometers. And our dots are grown by our postdoc Thomas Sarmiento at Stanford. These quantum dots have a three-dimensional confinement for electrons and holes, and strong optical interband transitions that nowadays are shown to be almost transfer limited from the line widths. However, they are grown in a random self-assembly process, so they are randomly distributed, and they have slightly different properties from dot to dot, so there's an ensemble broadening. But if you use a sufficiently low density of these, it's actually also an advantage, because then you can just use the very best of those. The cavities that we are working with are hexagonal linear 3-hole defect cavities that are patterned into a freestanding membrane. So in plane, we have a strong confinement of the photons due to distributive Bragg reflection. And out of plane, we have an index confinement, and that allows us to confine the optical mode to small mode volumes smaller than cubic wavelengths. What I particularly like about the about the semiconductor structure are that you can also couple these things to waveguides, and that recently also superconducting single photon detectors were integrated with other types of waveguides, so that all fuels the dream that that platform of quantum dots may actually at one point lead to fully integrated nanophotonic circuits. So the system parameters that are interesting for us are basically the same as this morning. We have cavity loss rates of kappa, we have a dipole decay of the quantum emitter, and a coupling between the quantum emitter and the cavity. And all these rates, in contrast to this morning, are of the gigahertz scale, so things are much faster because these things are much smaller. And also in these systems, we can reach the strong coupling regime where the coupling strength exceeds the system losses. And for the semiconductor platform, it's important to notice that the dipole decay is much smaller than the coupling strength. It's always the cavity loss rate due to the fabrication accuracy and designs that is limiting our approach, but nevertheless we can achieve strong coupling. In my talk I use the rates as energy decay rates and not field decay rates, so you might be aware of that. To probe these systems, we cool the samples to low temperature to have the confinement of the charge carriers in the dots. And the mainly used technique is cross-polarized reflectivity, which means we excite the system resonantly with a specific polarization and detect an orthogonal polarization such that we can detect the transmission through this cavity system, but in a cross-polarized setup rather than a technically more challenging transmission setup. And a typical experiment where we go to strong coupling is that we tune the quantum dot resonance into the cavity resonance, as you can see here with these lines. And a basic thing to do that is the lattice temperature, because they have a different dependence. And let me get these lines out of your way. As you can see, we can achieve a nice strong coupling here with parameters of cavity loss rate 18.4 gigahertz, coupling strength 12.3, and the typical dot decay rate is indicated here as 0.1. It's actually that small that it does not really matter how large it really is. We can use these systems for non-classic light generation, and similar to things that have been shown this morning, or also in atomic physics. This works with phenomena of photon blockade and photon-induced tunneling. So if we tune an excitation laser into resonance with the first rung of the Jaynes-Cummings ladder, due to the inharmonicity, it is not in resonance with higher rungs anymore, so we get preferentially single photon transmission. And if we tune into resonance with somewhat higher rungs, we get an enhanced probability for transmitting photon bunches or bundles. So to measure these nonlinearities, we use Hanbury-Brown twist type setups, where we split the signal into several arms with pulse shapers and measure then correlations on single photon counting modules. And to quantify, we mainly use the first order coherence. So, second order coherence. So if we do such an experiment, you can see in the blockade regime, at a time delay around 0, we get less counts than at cross correlations at other times. And for a bunching regime, we see a clear bunching peak. So all these spectra here are formed from those columns, because we do these experiments in a pulsed way, just because of the time scales of the system being much faster than the single photon counters. It doesn't work in a continuous wave approach, but the advantage is that it's then directly on demand, as we would use it for applications later on. Now, if we look at that process of photon blockade and photon tunneling again, and measure for the system in resonance the G2 function as a function of the laser detuning, you can see in the middle, like when we are in between the rungs, we do see bunching, and on the sides we do see anti-bunching. However, you have to see that in a typical system, the anti-bunching effect is very weak. We're just slightly below 1. And that's because the photon blockade is limited by the fact that the enharmonicity of the different rungs scales with square root of n, but the decay rate scales with n, because if you have more photons in the system, more photons directly scale to the decay rate. And in addition, in particular in the semiconductor approach, as I said in the beginning, it's mainly the cavity line width that's limiting. So we have a significant overlap of all these different rungs. And that's why also the strongest blockade is not observed when we are in resonance with the rung, but rather when we are already detuned to like 1.5 G instead of G, to minimize the overlap with higher rungs. So actually, what can we do about it? Well, we can fabricate better and better structures, but that's not a very physical approach. So one thing that we have ignored so far is the detuning between the quantum emitter and the cavity. So if similar as before, I plot the Jaynes-Cummings ladder and now photon blockade in resonance with the first rung and compare that to photon blockades at a given detuning, you can already see that here the mismatch is larger. So let's look at that in detail. One thing how you could excite higher rungs is a subsequent climbs up the ladder. So if you see here the first rung of the Jaynes-Cummings ladder, the subsequent transitions are the dashed and dotted lines for second and third rung. And you can see in resonance they are all quite close, but if we start to detune, the distance increases. And the same is true for an n-photon excitation of the nth rung, because that's here in solid for first rung, then 2-photon excitation of the second rung dashed, and 3-photon excitation of the third rung is dotted. So at resonance, all these transitions are very close, but if we detune the quantum emitter, they separate. Furthermore, because of these different decay rates between cavity and dot, you can see that if you look at the line widths of these transitions, for detuning also the lines get sharper. And I have to say here in that image, the to make it visible, the effect, the cavity decay rate is assumed ridiculously small. So with the realistic cavity decay rates, you have a huge overlap of first and second rung without detuning, but with detuning, the separation increases. So we expect photon blockade in these systems to be much stronger for a somewhat detuned regime. So we did the experiment. We start with dot and cavity in resonance. So there are the two polariton rungs, and in between we get the bunching. On the side we get the blockade. We simulate the thing in quantum optical simulations, and the result looks pretty much the same. That means our simulations seem to work. Now we start to increase the quantum dot and the cavity, so that the two polariton transitions evolves, and the one that is more dot-like, the photon-blockade dip gets deeper and deeper and narrower, and that's also reproduced in the simulations. So for this specific sample that had a G2 of only 0.95 in resonance, at the detuning of a few G, we approach something that's of the order of 0.45, so it's even below that threshold of 0.5 and much better. So far we have only looked at the G20, which is a quantity that is nice to measure because it's insensitive of losses, but it doesn't tell you very much about the actual number of photons that are in a transmitted pulse. So we want to simulate that, but since we only have a G20 so far, that's pretty bad to compare like only one parameter to simulations. So we did additional measurements of the third order coherence by adding in more beam splitters and more single photon counters to get more quantities as fitting parameters for the simulations. And if we now compare the measurements of G2 and G3 for the dot and cavity in resonant case with a detuned case here of 3G, you see that the experiments and simulations match quite well. So that allows us to do simulations with these parameters with a quantum jump method, where we can like detect the number of photons in an output pulse, and by doing quantum Monte Carlo, we get the probabilities for specific photon numbers to be in the transmitted pulse. And you can see here in the resonant case where the G2 was about 0.95, it's still quite significant contributions of 2 and 3 photon states at the position where the lowest G2 is. So it's not really single photons, it's mainly a coherent state with a little bit more single photon character. In contrast, in the detuned case, we get a huge peak for the single photon, some 2 photon probability, and 3 photons are almost entirely suppressed. And that was just typical system parameters. With better parameters, we can get nice single photon sources. Now, one thing that we have neglected so far is the lifetime of the states compared to the pulse length of our laser that we use to measure G20. And if the pulses are too long, longer than the polariton lifetime, we will re-excite the system. So there's a probability that with one excitation pulse, we do get 2 photons out, but in 2 separate processes. Whereas if we make the pulse too short, we have an increased overlap because of the spectral width to higher rungs. So if we look at the relevant time scales, the lifetime of a quantum dot that's far away from the cavity is about 10 nanoseconds, because in the photonic crystal it's per cell suppressed. And from the quality factor of the cavity, we can extract an energy lifetime of about 8 picoseconds. So in resonance, we have a polariton lifetime of 16 picoseconds. And if we now look at the decay rate simulated from just taking the different rates here into account, you see that it pretty fast increases to longer lifetimes, allowing longer laser pulses to be used. But I have to insist that here we are in a semiconductor platform at a finite temperature, so we do have a very strong coupling to phonons, and that coupling to phonons is known to cause a population transfer from more cavity-like polaritons to the more cavity-like polariton. So in order to measure the real lifetimes and the coupling strengths to phonons, we did time-resolved measurements on a streak camera where we resonantly excite one of the branches and monitor the time traces from the 2. And because it's a streak camera, we have sufficiently high precision to extract the small lifetimes. So if we now compare the calculated lifetimes with the measured ones, you can already see on the numbers here that they are much faster. So we simulated these lifetimes with an effective phonon master equation approach, and used that approach to fit the data and extract the spectrum of the polariton to phonon coupling in these systems. So indeed, we have a strong reduction of the polariton lifetime due to the coupling to phonons, which efficiently transfers the long-lived, more dot-like excitons to the very short-lived cavity-like polaritons. So if we include these things into our simulations, we can actually set out and simulate how good is the best G2 that we can achieve for a specific detuning of the polariton branches. Here it's like 4G detuning between laser and cavity. And you can see here that as a function of the pulse length and the laser detuning, we do observe a global minimum for the simulations. And you already see that there is a difference if you do not include the phonons. The G2 values that are expected are lower and they are a little bit shifted. So to confirm that these simulations are accurate, we did measurements with several different pulse lengths. And here it's particularly interesting to see if quantum dot and cavity are in resonance. The best blockade is observed for smaller, shorter pulse lengths because of less re-excitation. But if we detune, we can use longer pulses to get lower values. So high fidelity photon blockade requires to choose an appropriate detuning between cavity and laser, and to achieve use a corresponding pulse length of the probe laser. And all in all, we've achieved photon blockade experiments with G2 as low as 0.2 with these systems. So now the coupling to the phonons can also be exploited for different schemes that are otherwise like hardly to access. For example, we can excite one of the branches and frequency filter the light that is emitted from the system to only select photons that come, in that case, for example, from the cavity. So we excite the dot-like polariton, we detect from the cavity-like polariton, and if we use a laser pulse that is much shorter than the polariton lifetime, we are able to coherently control the population of the polariton, as you can see on these Rabi oscillations here. And if we now use a pi pulse to excite the system at a specific detuning and measure the G20 of like the detuned phonon-assisted emitted single photons, we observe a reasonably good G20 with a measured value of 0.03. So that means by exploiting the phonons, we can improve things even a bit more and get reasonable single photon emission from the system. So I'd love to talk about these non-classical light generation topics more, but I should move on to also talk about our other projects that are going on. But I'd like to mention that single photon emission is not the limit of strongly coupled systems. For example, there was a recent proposal from our collaborators from the Universidad Autónoma de Madrid in the group of Fabrice Lossi, where they proposed a specific excitation condition of a strongly coupled system that results in the emission of n photon bundles. So you can tune the system not to emit single photons, but to emit almost exclusively 2 photon packages or 3 photon packages. So if you're interested, you might check out that proposal. So as you have seen, all the lifetimes in the slides before that I've shown were really small. So for kind of more sophisticated quantum networks, it's impossible because you need reasonably long lived states with reasonably long coherence times. And one advantage or one possibility to realize such a quantum node with quantum dots is to use charged quantum dots, where you use the spin of an excess charge, which can be in the hundreds of microseconds coherence time, which if you place it in a magnetic field in void geometry, you get that non-degenerate double lambda system, where you can have 4 optically allowed transitions that can be used for spin initialization, for optical coherent control, or also spin photon entanglement. And here's the example of one quantum dot that was delta doped to get the excess hole. If you look at the polarization of the emitted light under non-resonant excitation, you can clearly identify all 4 of these transitions. So I'm pretty sure that in a few minutes Ido will talk about what you can do with such charge dots in photonic crystal cavities. So just let me quickly point out another material system that we've been recently looking at. and those are site-controlled nanowire quantum dots. The material is provided from our collaborators, Walzwiller and Michael Reimer in Delft. And these wires are grown by CVD, and you have a single quantum dot in each of these wires. And if you put them in a void magnetic field, you also get such a double lambda system for all 4 transitions for any of these wires. And that's an example of non-resonantly excited PL series measuring as a function of the magnetic field, and you do see the Siemens splitting with the 4 lines appearing. So the first thing to demonstrate in such a system is spin pumping. So that means you park your laser on one of the transitions and observe luminescence from the excited state to one of the ground states. And if you would just do that, you would see basically not much, because as soon as you have shuffled your spin into the other ground state, you don't get signal anymore. But if we do this, so that's what we measure here, but if we do the same experiment, so we scan the laser over one of the resonances, while at the same time having a non-resonant excitation pulse that acts as a randomization of the ground states, we can clearly resolve these resonances, and we can do that for pumping any of the 4 transitions. Right, so much for quantum dots. In Yelena's lab, we're also investigating different types of material systems, and the material system that we started to look at a couple of years ago is silicon carbide. As you might know, there are a bunch of quantum emitters or defects in silicon carbide that were shown to exhibit coherence and also coherent control and even room temperature coherent control. And so we started to fabricate cavities out of the system. And for cavities, the polytype 3C is particularly interesting because that one can be grown on silicon. So that allows to perform an under edge of the silicon to obtain freestanding structures like photonic crystal cavities, where we obtain quality factors of 1,000, or nanobeam cavities, which have quality factors of around 1,500, and that were all in the infrared wavelengths. Recently, we also fabricated micropillar structures that were small enough to facilitate TE and TM modes in the visible wavelengths range to couple to potentially interesting emitters there. And here we achieved resonances with quality factors as high as 2,300. So now that we have silicon carbide as an interesting material system, we also try to build a hybrid approach between silicon carbide and diamond, because of all those well-known quantum emitters in diamond. And for that approach, our collaborators at Stanford managed to grow nanodiamonds on silicon carbide by CVD growth of diamondoids that consists of just a few carbon atoms. And that growth fortunately works on 4H silicon carbide as well as on 3C silicon carbide. It can be grown with different sizes of only a few 100 nanometer to a few microns. And surprisingly, the growth does not only work on bulk, but we can also grow on nanostructures themselves. So this year we first fabricated that nanobeam cavity from silicon carbide and then grew diamond on that structure. And so it's all just very preliminary results, so we haven't had the time to investigate these things in more detail. But here the growth was also random, but with that technique you could also imagine to just site selectively first fabricate your nanostructure and then grow a nanodiamond on top. And since diamond is a very hard material, we can use those nanodiamonds also as hard masks for etching. So for example, in 4H, which is the bulk polytype of silicon carbide, we can etch pillars with a diamond on top. And here on the 3C silicon, where we can undercut, we managed to fabricate the things that we called nano mushrooms that have the nanodiamond on top and then consist of a microdisc in 3C silicon carbide on a silicon pedal steel. So you might ask now, well, that's all nice, but how do we get the quantum emitters in there? And the interesting thing, that we learned when looking at the system with the PL setup is that we get them for free. So we did spatially resolved PL measurements and saw that the nanodiamonds grown on silicon carbide exhibit a strong luminescence that's at room temperature that matches with something that is known as the silicon vacancy in diamond. And the hypothesis is that due to the growth of the nanodiamond on the silicon carbide, there is a chance that silicon from the substrate is incorporated into the diamond. And for the silicon vacancy, it's known that at low temperature it exhibits such a double lambda system without the magnetic field. And we haven't done the experiments yet, but we hope that once we go to low temperature, our nanodiamonds that are then in these photonic nanostructures will be useful for these kind of systems. So far, all the cavities that I have shown to you were some kind of designed by humans. So somebody had the idea of, okay, we could omit holes to fabricate a cavity in this L3 photonic crystal, or do nanobeam cavities and all these kind of things. And after somebody had the idea, computers, simulations were used to, like, for example, shift around the holes here to make the quality factor higher. So Yelena's lab asked some time ago if there's like a way to do that more efficient. And in general, what you would like to have on a nanostructure is a good performance, a small footprint, robustness against fabrication errors and temperature variation, probably novel functionality, and it should be with as less human input as possible. So they developed a design algorithm that takes constraints like what can be fabricated into account, and what you do is you only specify your input and output parameters for linear nanophotonic devices, and then let the code completely develop an own structure that does that in the best and most stable way. And recently we demonstrated a broadband demultiplexer to separate 1300 and 1550 nanometer light. So that's how the fabricated structure looks like. That's a simulation of the field evolution for 1300 and 1550 nanometer light. In the simulation of the transmission, you can see a large extinction ratio and very little crosstalk. And when we fabricated the structure, we were surprised ourselves how well it matches the simulations. And moreover, from looking at the number of 10 different samples or so, you can see in this light red here the variation from sample to sample. So the algorithm seems to be really stable against fabrication inaccuracies. And the result is a small footprint of only 2.8 times 2.8 micron, a low insertion loss of the order of 2 decibel, low crosstalk below minus 11 decibel, and a wide bandwidth operation. And we hope that these kind of algorithms will help to change the future of nanophotonics, to come up with like many weird devices in addition to the wavelength demultiplexer that we have already demonstrated in experiment. There are also mode converters, mode demultiplexers calculated, and also 3x3 hubs, and probably you can come up with additional applications for such an inverse design algorithm. So in summary, I have shown you that benefits of detuned photon blockade, ultra-fast dynamics of strongly coupled systems, spin initialization in a nanowire quantum dot, some recent results on our silicon carbide and hybrid silicon carbide diamond nanostructures, and the inverse design algorithm. Let me quickly acknowledge the people that did the work. So in quantum dots, it's Konstantinos, Thomas, Kevin, Armand, Yusuf, and Konstantin and Peter McMahon. And the work on silicon carbide is mainly done by Tom, Marina, and Linda. And inverse design, the main people are Alex and Jan. Finally, thank you for your attention.
Thanks, Kai. Are there any questions?
So, do you think that there are any prospects to using this inverse design strategy for designing like better photonic crystal cavities?
We hope so. So we have just started to work on that, but one of the things that we could imagine is that for example, the L3 cavity is a high Q cavity, but the thing is, by optimizing the Q factor, you one of the ways to look at is that you create kind of interference that like cancels out your emission in C direction. So you get a high quality factor, but you get a really bad collection efficiency with a standard microscope objective. So if your numerical aperture is limited, because your most of your light is then emitted at high K vectors. So we hope, for example, that one of the things that we try to work on at the moment are photonic crystal cavities where the output goes into specific output modes. Or also waveguide coupled photonic crystals. You could also imagine that thing to be optimized by such an algorithm.
Concerning the first part of the talk, do biexcitons play any role here?
No, they don't, because the detuning here is of the order of a few G, which translates to something like 100 microelectron volts, and the typical detuning from exciton to biexciton in these samples is 2 millielectron volts. So they are so far apart that they don't play any role. I have ideas of like exploiting biexcitons in these systems for initialization processes and so on, but for these processes, they are just too far away.
Maybe just thinking of more technical part. But what you do is actually you target one end of your photonic cavity for input and use the other one for output?
No, it's a cross-polarized suppression. So
you avoid targeting the dot itself, or?
So the coupling to the dot is, in and out coupling to the dot is in that case entirely through the cavity, because the cavity has such a larger oscillator strength than the dot. Even when you detune it, the emission of the dot is that doesn't play any role, and it's just through the detuned cavity. We have shown that that's true for detunings up to 60 or 100 G.
So can you also design the phases of this? I mean, what do you have to specify there? Because like the transmittance, the phase of it, what
so the thing that is specified in the standard algorithm is you have a number of input modes and a number of output modes, and what you define is the field in intensity in like specific modes, that at each output you have a number of modes at each input, so you specify like your input and then specify which modes in the output you'd like to have populated. I'm not sure how if that would work for phase as well.
So it's not amplitude, it's intensity that you can inverse design.
I think, yeah.
I have a question about that design as well. Like, how long does it take to kind of, I mean, if you start the computer, how long does it take to go from beginning to end?
I've not done these simulations, but I think it's of the order of a few hours, at least on our cluster.
So if there's no more questions, let's thank Kai again.